Hi there and welcome from Ventura, California to today's webinar, The Role of GNSS Antennas in Mitigating Jamming and Interference, sponsored by Novatel and Inside GNSS and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they provide an overview of signal processing for adaptive antenna systems and discuss key factors involved in integrating beam steering antennas with GNSS receivers. You'll also have an opportunity to have your questions answered at midpoint and at end of the presentation during the Ask the Experts panel session with both panelists. Now, we've invited you, along with over 500 professionals registered from 53 countries, representing 30 states and provinces across a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Before we get started, Glenn Gibbons, editor and publisher with Inside GNSS, would like to take a moment to welcome you and to introduce Neil Guerin and Mark Petavello, who will be moderating the main portion of today's webinar. So over to you, Glenn.
Thanks, Lori, and a warm welcome to our viewing audience to this latest installment in the Inside GNSS web seminar series. Today's presentation is sponsored by Novatel and addresses a subject that several past Inside GNSS webinars have already touched upon: interference and jamming of GNSS signals. Our discussion today will focus on the role of antennas in mitigating the effects of interference on GNSS receivers. I encourage those of you viewing our presentation today to contribute to the webinar as well by responding to the questions in our online webinar polls and sending in your questions for the live question and answer periods that will take place during the event. And now I would like to invite Neil Guerin, Defense Product Manager for Novatel, to say a few words about today's event.
Thank you, Glenn. It all starts at the antenna. There are numerous techniques to mitigate against intentional and non-intentional interference, each with their own merits. But as you will hear today, mitigating interference at the antenna is one of the most powerful ways to protect your position, navigation, and timing solution. Novatel provides a number of highly effective antenna solutions, including our high-performance pinwheel family, the gadget anti-jam antenna, and a host of diverse antenna solutions from our subsidiary Antcom. Novatel is pleased to sponsor today's webinar, and we are sure that you will enjoy the following presentation by internationally recognized subject matter experts, Dr. De Lorenzo and Dr. Gupta. Back to you, Glenn.
Thanks, Neil. Our moderator for today's web seminar is Dr. Mark Petavello. Mark is a professor in the Position, Location, and Navigation Group in the Department of Geomatics Engineering at the University of Calgary in Canada. Mark has been actively involved in the navigation community for more than 15 years and has received several awards for his work. Mark is also the contributing editor for the GNSS Solutions column of Inside GNSS magazine. Mark, it's great to have you with us here again today. Welcome.
Great, thanks a lot, Glenn. I'm happy to be back, and welcome to everybody out in the virtual audience. We have two very well-respected experts in the areas of interference, jamming, and antenna design. And before we get to them, though, I wanted to, first of all, give a little bit of context as to how this seminar fits into previous ones that have been offered by Inside GNSS. And for those of you who followed along last August, we had Tom Stansel and Logan Scott give a really excellent presentation on interference. The focus there was on the types of jamming and spoofing, as well as some of the possible sources that go along with those. And at the same time, they presented several different approaches as to how you might be able to mitigate that. And this particular presentation today is going to be looking more at one specific approach, which is how to use multi-antenna systems, which, as Neil mentioned just a few seconds ago, has been proven to be very effective. And so what we're going to look at, without giving away all the details, of course, is a look at the different types of antennas and receiver configurations, some of the practical considerations you might want to take into account when you're selecting an antenna and or putting them together in an array, some test results, and obviously some outlook for where our experts think this might be going in the future. So that's the plan, but before we get there, I'll turn it back over to Lori to have our first poll question. Lori.
All right. I'd be happy to do that, Mark. Coming up on your screen in just a moment is that first poll question, and if you would weigh in, are you aware of ever having your GNSS receiver jammed? And is it yes, no, or maybe you've suspected it, but you can't be sure? Okay. And looks like we have 44% saying yes, 39% saying no, and 17% suspecting but cannot be sure. Any thoughts on those poll results, Mark?
Well, I think that speaks directly to why there is such an interest in these particular approaches of dealing with interference, antennas just being one of them. So hopefully the 44% of you who said yes and perhaps the 17% of you who weren't quite sure are going to gain some valuable insight that's going to help deal with that going forward. So having said that, I think we can start introducing our presenters. And the first one is Dr. David Lorenzo, who is a principal research engineer at Polaris Wireless and also a visiting scholar at Stanford University's GPS Research Lab. His current research focus is in the multi-sensor mobile location, adaptive beam steering antenna arrays, and navigation systems, security, and integrity areas. He received his PhD in aeronautics and astronautics from Stanford and has previously worked for Lockheed Martin and Intel Corporation. He has several patents and has co-authored several papers in this area, so he's very well suited. And David's going to start us off today by talking a little bit about the general problem, some of the types of antennas, and the integration with receivers. David, it's all yours.
Thanks, Mark. Hi, everyone. Good morning. The fundamental problem we address in today's webinar is how to track GPS satellite signals while rejecting interference. And it's in this context that we nearly always talk about multi-element and adaptive GPS antenna systems. Now, of course, there are a number of different anti-jam methods available to our community. These methods include inertial sensor integration, adaptive digital filters, pulse blanking or time gating, integration with other radio navigation or even telecommunications signals, and vector tracking of the GPS or GNSS signals. So clearly our discussion of beam steering antenna systems, as Mark said, lives within this larger domain. And I mention this now both to acknowledge it as well as to dispense with it for the remainder of the webinar. As you can see here, there is a hierarchy of complexity as well as anti-jam performance among GPS antennas. We'll talk about these each in turn. The simplest antenna for a GPS receiver is a single element fixed reception pattern antenna, or FERPA. This class of antenna is what is in most common use today for everything from high performance survey systems to aviation and marine navigators to your smartphone or personal fitness watch. This antenna has no ability to modify its receive pattern in order to account for changing RF conditions. In other words, its gain response is fixed. The next class of antenna, while still technically a FERPA, is one which is designed specifically to limit receive power from some aspect. What is shown here are multipath limiting antennas, which are optimized for sharp attenuation of receive power for signals coming from below the local horizon. A substantial evolution beyond this antenna class is a switchable antenna system, or selective Nullor. What you see here is a dual element stacked patch antenna developed here at Stanford University some 10 plus years ago. What this antenna does is to allow switching of the signal path from a nearly isotropic wide angle receive element during benign signal conditions to a narrow beam element, which implements what's called a half wavelength trap during stressed signal conditions or interference. This narrow beam element not only forsakes reception from below the horizon, but also gives up signals at low elevation angles, in effect trading off satellite geometric diversity, or GDOP in our parlance, for over 10 dB of improved rejection at directions from which jamming signals are likely to originate. We move now into the classes of antennas which are known in the industry as Serpas, for controlled reception pattern antennas, or sometimes controlled radiation pattern antennas. The first example I show here is an adaptive Nullor. This antenna reacts automatically to the sensed interference environment and attenuates or steers pattern nulls towards jammers. Commonly, the objective is that the output signal should exhibit particular desirable spectral qualities. For example, it should resemble a white noise process. The signal which comes out of an adaptive Nullor, such as this one, often has been conditioned so that it can feed directly into the antenna port of an otherwise unmodified GPS receiver. Similar to an adaptive Nullor is a beamforming Serpa. Beamforming employs constructive interference to enhance a signal from a particular direction, a particular desired direction, just as the adaptive Nullor employed destructive interference to attenuate undesirable signals. In this picture, you can appreciate that the propagating signal wavefront from the satellite arrives at the right-hand antenna earlier than it arrives at the left-hand antenna. If we were to perfectly time shift or delay that earlier signal, then the two signals would add up. Thermal noise, which is uncorrelated, would increase only by square root 2, and we would have achieved our objective of enhancing the received signal-to-noise ratio, or SNR. In practice, the time shift is actually implemented as a phase shift, or phasor rotation. This is why the constructive effect is perfect only at the center frequency of the signal, and it falls off away from that frequency. You also see that for each antenna element we add to our array, we pick up another degree of freedom in how the signals can be combined in order to enhance desirable signals or to attenuate undesirable signals. We say that our degrees of freedom scales approximately as the number of antenna elements minus 1. Finally, the spatial selectivity or directionality of our antenna array also scales with the number of elements. This is an important consideration when we think about the spatial distribution of satellites and jammers. Now, as we add elements to our array, either we can synthesize more beams or we can achieve greater gain in one particular direction. What you see here are the array gain patterns for a 7-element array when pointing the main beam of the array in several different directions in turn. The middle row of figures represents a 3D view, while the bottom row of figures shows a projection of the upper hemisphere gain onto a polar plot. This latter is a fairly common visualization method, and you can see how the main pointing direction shows up clearly as a bright red region, while pattern nulls appear as bluish bands or spots. We come back now to an adaptive array. Remember, before we talked about adaptive nulling. And in this case, we have the general objective of controlling both beams and nulls. So our adaptive beamforming and null steering Serpa senses and reacts automatically to the RF environment in order to adjust the weights, meaning the amplitude and phase rotation, of the individual antenna signals. Essentially, the amplitude and phase of each signal are under individual control, as you see illustrated here. And the signals are combined into a single composite output signal, which then feeds downstream processing blocks. In our case, these downstream processing blocks are in fact the tracking loops of GPS receiver. There are a wide variety of adaptation schemes available to us as signal processing engineers, and as well there are pre-processing schemes that can improve convergence or stability properties. As an example, one adaptive algorithm is the minimum variance distortionless response array algorithm, or MVDR. This algorithm constrains to unity the array gain in a particular look direction or directions, while rejecting coherent interference down to the noise floor. The MVDR array also may have side constraints for null steering. Next, we come to the topic of space-time adaptive processing, or STAP, and space-frequency adaptive processing, or SFAP. This basically extends the concept of spatial-only beam steering, which we just covered, to include temporal or frequency domain extent in our beam steering. Remember, when before we were talking about the phase shift of the antenna signals being optimal only at a single frequency, this also meant that jammer cancellation also was only optimal at that single center frequency. Now, by including a spectral dimension in our beam steering, we have more control, more knobs if you will, to shape the response of the array. This will be important, as you can appreciate, for wideband jamming signals. It also gives us some measure of control in modifying or reducing the effects of distortions that may have been caused by non-ideal characteristics in our array elements or analog electronics. Of course, this all comes at the cost of even greater complexity compared to the previous classes in our hierarchy. The final two spots in our list, the all-in-view adaptive Serpa we'll cover in the next section, and the vector tracking adaptive Serpa is a topic that's kind of beyond the scope of this introductory webinar. So let's shift gears a bit and address the issue of integrating a beam steering antenna with a GPS receiver. After all, an antenna array is of only academic interest to us if we can't employ it to improve the receiver's availability or robustness to interference. We're going to start with what I expect many of you may be intimately familiar, a single channel of a GPS receiver's signal processing internals. I show this just to level set us to a common baseline. For our purposes, it's enough that we keep in mind that RF energy enters the antenna, gets conditioned and then converted to discrete time digital samples, and finally is processed in the receiver in order to recover time of arrival, navigation data, and so on. When we substitute for the simple single element FERPA shown on the previous slide, with this multi-element Serpa, the conceptually simplest way is to keep the antenna subsystem fairly distinct from the remainder of the receiver. That's what you see here. The beam steering occurs completely upstream of the receiver's tracking functions, and there is no feedback per se no connection per se, between the receiver proper and the Serpa. This architecture could represent a power minimization adaptive nuller, such as we talked about before. All the antenna subsystem really does in this case is to null steer in the direction of an RFI source or sources up to the degrees of freedom of the array. This represents actually quite an effective anti-jam solution in terms of minimizing interference power. One drawback of this system, as you may have already appreciated, is that the beams of the array are not controlled and consequently may or may not be well placed with respect to the satellite constellation. Parenthetically, of course, as the constellation gets larger, then this trade-off becomes less serious. On the other hand, with significant occlusions, such as in mountainous terrain, this architecture may become less attractive. If, on the other hand, we can constrain the antenna pattern, implement true beamforming in other words, then the antenna array can allocate or spend some of its degrees of freedom in maintaining gain or constructive interference towards satellites, while also null steering to interference. In other words, an adaptive beamforming and null steering Serpa. Now, one way of determining our beamforming constraints is to utilize knowledge of array geometry, platform orientation, and the satellite constellation ephemeris. These are the solid lines connecting the inertial subsystem and the navigation data recovery subsystem to the weight control algorithm. It's also possible to constrain the beamforming operation using known characteristics of the received signal. This would be the dashed line in the figure, one variant of which is sometimes termed blind beamforming. So what you see here on this slide now contains pretty much all of the high-level conceptual ingredients of a beamforming and null steering antenna array fully integrated with the GPS receiver. We're not quite done yet, of course, but at this point we're well on the way there. Now, that was showing an adaptive Serpa and a single satellite tracking channel. But of course, a GPS receiver doesn't track just one satellite, it tracks a multiplicity of satellites. Modern receivers may contain dozens of tracking channels in order to support multiple GNSS constellations and 2 or more frequencies. And to think, a single frequency receiver performs all of its signal processing and navigation magic from a single tenuous antenna and RF chain. Now, when we reimagine our adaptive Serpa, you can see truly how the output from the beamforming operation may be feeding the same identical composite output signal to all of the receiver's tracking channels. This is why we drew the distinction before between the unconstrained adaptive nuller, which minimizes interference power but does not control array beams, and the constrained adaptive beamforming and null steering Serpa. To be clear, the adaptive nuller is advantageous in terms of minimizing the complexity of interfacing the beam steering antenna subsystem with the remainder of the receiver. Upgrading from a FERPA to an adaptive Serpa may be as simple as unscrewing and rescrewing the antenna cable. We close this section by addressing and solving the dilemma of how to control the gain to many satellites simultaneously, many more satellites in fact than the degrees of freedom of the array would indicate we could support. And we do this, perhaps not so surprisingly, by allocating a separate weight control block for each receiver tracking channel. Now, this could be considered computationally expensive. After all, we're performing a bunch of matrix multiplications and, depending on how it's mechanized, perhaps even matrix inversions as well. But don't forget also that due to Moore's law and the ever-increasing computational power we can bring to bear on problems such as this, that what was inconceivable even a few years ago now finds an easy computational solution. In fact, later we'll see a receiver that does all of this and more, totally in software, using readily available consumer building blocks and running on an off-the-shelf general-purpose CPU. And finally, this has pretty much all of the high-level details of interest to us today. We've covered quite a bit of ground, but of course we're not done yet. Anyway, I think I'll close this section here and turn it back over to you, Mark.
Great, thanks a lot, David. I'll introduce Dr. JD Gupta, who is a research professor in the Department of Electrical and Computer Engineering of the Ohio State University, and he's been there since 1979, so obviously a lot of experience, and that's reflected by the fact that he is a fellow of the IEEE, a fellow of the Institute of Navigation, and an Edmund S. Gillespie Fellow of the Antenna Measurement Techniques Association. He's also the recipient of that latter agency's Distinguished Achievement Award in 2007. His research interests include radar imaging, EM scattering, antenna test range technology, and adaptive antennas and geolocation techniques, So JD is very well suited to give us a presentation, and today he's going to be starting off by talking a little bit about some of the considerations when using and or selecting antennas for your array. JD, it's all yours.
Thank you, Mark. Hi, everybody. Dr. Lorenzo talked to us about how to use adaptive antennas with GPS receivers. He also talked about various ways to control the weights of adaptive antenna. He alluded to that the performance of an adaptive system depends upon the antenna array in terms of how many elements you have. So what we are going to talk about, how a good design of antenna array itself can affect the performance of your complete system. So as David pointed out, how we control the weights of various antenna elements, what kind of interference environment we have, also what kind of physical antenna array we have will dictate the complete performance. And what I want to say here is antenna is the beginning part of our complete system. If you don't have a good start, don't expect that the performance will be very great. You can do a lot of signal processing, but if you got a bad antenna design, you are not going to get the best results. So in the next 10 or 15 minutes, I'm going to talk about what kind of things we should be careful in getting a good antenna. As you know, when we talk about antenna array, there are 3 or 4 things we talk about. One is aperture size. In that given aperture, how many elements we have, how the elements are distributed. Also, is that antenna planar or non-planar? Finally, what kind of elements we are using in this antenna array. So if you talk about these 4 things, basically you cover the complete antenna array. So let's start with aperture size. First is, what is aperture size? When an antenna person says aperture, what they're talking about, what is the biggest footprint of this antenna? So if I'm looking at a planar antenna, that itself has an aperture because that is the biggest aperture. If you got a concave or convex antenna, then you see from a certain angle and see when you get the biggest footprint, and you define the aperture of the antenna. For the best performance, you want an antenna array with large aperture. The reason for that is, in adaptive antenna, in the presence of interfering signal, we are going to put nulls in the direction of interfering signal. Once you put a null in certain direction, you're going to lose a satellite signal also from that angular region. If your aperture is small, you're going to lose quite a bit of angular region around the interference direction, so you'll be losing more and more satellites. If you got a large aperture, you will be coming out of that null very quickly, and you will be losing less number of satellites. And you can see the same thing in the 2 plots I'm showing in this chart. These charts are showing the signal to noise ratio over the whole upper hemisphere in the presence of 2 interfering signals. The center of the circle is zenith, outside is the horizon. And we have put nulls in the jammer direction, and you can also see in the process of putting nulls in the jammer direction, some of the area signal to noise ratio has dropped. If you compare the plot on the left with the plot on the right, you can see as I increase my aperture, same number of antenna elements, everything is all the same. I just increase the inter-element spacing to make the aperture large. I'm coming out of those nulls very quickly. That means I will be losing less number of satellites. So if you have a choice, you want to get a large aperture so that you don't lose too many satellites in the process of nulling an interference signal. So now we got an aperture. The next thing is how many elements I should put in this aperture and what should be the element distribution. First thing you want to make sure is that you have enough elements in the aperture that you don't cause what we call is grating nulls or sympathetic nulls. So what do I mean by this grating nulls? If the inter-element spacing is large, in the process of putting a null in the interference direction, you can also get a null in some other direction, and which is a no-no because you're going to lose the satellites which are away from the jammer because you got a null in other direction. To limit these nulls, the inter-element spacing should be less than half a wavelength. Like in the plots I'm showing in this chart, you can see I have a jammer and I put a null in the jammer direction. But in all other areas, I'm looking good. Now, if I increase the inter-element spacing so that to make the aperture large, I have a very sharp null in the jammer direction, but I'm getting these sympathetic nulls. So if the satellites fall into these areas, we are going to lose that as satellite also, and we don't want that. And that's the reason you want to keep the inter-element spacing small. Now, there's a dilemma right now. We want a large aperture, and I'm telling you to put elements close to each other. When we do that, the power requirement, the cost of the adaptive antenna, weight, all those things will go up. So in that case, you may have to remove, or what we call thin the antenna array. You may want to remove some of elements so you can still meet your power, weight, and cost requirement. Thinning is an art. We can't get into the details of that. Antenna literature is full of it. If you really get into the problem of thinning an antenna array, I would rather say go to that literature. But one comment I will make is the rule of thumb when we do the thinning. Let's say I got a fully filled aperture and I have certain kind of main lobe and certain side lobe. As you start thinning your antenna array, the side lobe will start coming up. And you want to make sure that side lobes still stay about 5 to 7 dB below the main lobe. If you start going further than that, it's a bad thinning. So that's a rule of thumb. Fortunately or unfortunately, in our case, we don't get a large aperture because we have to put these GPS receivers on a smaller platform, which may be handheld, UAVs, small trucks, small planes. So we don't have luxury of getting a very large aperture. Our sponsor, they give us a very small area, and that's where they want to put adaptive antenna. So what do we do when we got a small aperture? Since we are dealing with a small aperture, the first thing we want to do is pack it up, put lots of antenna elements, because when you put lots of antenna elements, you get more degrees of freedom, as David pointed out. That means you can do more in terms of nulling and beamforming. That's a good idea. But you need to be careful before you put lots of antenna elements. First thing is, in a given aperture, if you add more antenna elements, you're not going to improve your resolution because the aperture dictates the resolution. Second thing is, when you put lot of elements in a given aperture, there's going to be strong coupling between the antenna elements. And this coupling can be hard to deal with. What I'm trying to say here is, first thing is, let's say we are doing simple null steering. If I'm coupling between the antenna element, a single antenna element may not provide the whole upper hemisphere. So we have to go to some other means to obtain upper hemisphere coverage. So that's one thing. If you're going to do beamforming / nulling, then coupling can be taken care of. In that case, you don't have to worry too much about it. But the last point, which is more important, is antenna-induced biases. As you know, antenna does induce biases, and we have to, for precision application, we have to correct for those biases. In adaptive antenna array, these biases depend on the interference environment. They change with the interference environment. So if you got a very strong coupling and you start nulling, the bias is introduced by the antenna in the absence of interfering signal, in the presence of interfering signal can be very different. So you have to do calibration on the fly, and you have to be careful about that. So here is an example to show you what the coupling does. I have a 6-element antenna array. The total aperture is about 4 to 5 inches. If I have no element around a given element, so basically I have a single element, you will get the coverage as I'm showing on the top left plot. And we are getting fairly good coverage of the whole upper hemisphere. However, because of the coupling between antenna elements, an individual antenna element will give you this kind of coverage. And you can see now I don't have a good coverage over the whole upper hemisphere, which is a no-no. So if I'm going to use this antenna array as a nuller, I have to come up with another scheme. And the scheme we came up with is given here. What we do is, because the total aperture is small, we combine all the antenna elements to get a fixed gain along zenith. And by keeping the gain fixed along zenith, then we do the nulling part. So that is one way to make this antenna work as a nuller. So what did we learn about number of antenna elements and distribution? First thing is, please do not put the antenna elements more than 4/10 or 0.45 wavelength apart, because you will get grating lobes. And once you got a completely filled aperture, element distribution really doesn't make a difference. You can move the elements around, you will get the same kind of performance. Finally, how many elements can I include in a given aperture will depend upon size of individual antenna elements. You have to make the elements very, very small if you want to pack them together. Also, as always, power, weight, and compute cost will drive the factor also. So how many elements I'm going to have in an aperture will be dictated by these parameters. I'm going to stop here so we can take some questions. Back to you, Mark.
Great, thanks a lot, JD. As JD mentioned, we will be taking questions, but just a reminder again, if you do have any, do enter it into your control panel on your screen, and we will try our best to get to them during the session today. We will start off, actually, David, I'll pass the first one to you, and in your part of your presentation, you talked about a weight control algorithm, and I was wondering if you could give some idea as to how the computational requirements for that compares to the rest of the signal tracking channels.
That's a good question, Mark. Thanks. So there's two pieces in the weight control for an adaptive array. One piece is observing and estimating the interference environment, and the other is then using that observation to select and null out sources of interference. And so those are both fairly computationally intensive. The estimate of the noise environment plus the inversion of that covariance matrix to develop a beam steering weight vector. Those are probably comparable to the amount of processing in a receiver tracking channel. Of course, instead of a 1 or 2 bit signal on a traditional receiver now, because it's an anti-jam receiver, you're talking about much more bit depth. You may have 12, 14, or 16 bit samples coming in. So it is significant. And it's probably one of the reasons that the complexity of an anti-jam beam steering receiver is quite a bit higher. Thanks, Mark.
Great, thanks a lot, David. The next one, Judy, is for you. Someone asked the question, can multi-antenna systems be used with linearly polarized antenna elements, such as those commonly used in commercial applications?
That's a very good question, Mark. Yes, you can use a linearly polarized antenna as an adaptive antenna. The only thing is you may lose some performance in terms of reception of satellite signals, because incoming signals are circular polarized, and you have a linear antenna to receive those signals. So if you can tolerate that much degradation in the satellite received signals, there is no reason that you can't use linearly polarized antenna for adaptive processing.
Excellent. Thank you very much. The next question was sent in by Srinivas. I'll direct this one first to you, David, but Jitty, you might want to chime in a little bit later. The question is, given that a majority of GNSS receivers these days are in cell phones, and given also that the size of one is one of the important concerns, and I assume that's reference to the aperture, do you recommend, or perhaps do you suspect, signal processing methods over appropriate antenna design for interference mitigation?
Thanks, Mark. So that's very interesting. As we know, cell phones and GPS receivers, the small commodity GPS receivers for cell phones are driving a lot of the market. Certainly not at the high end, but these are produced in hundreds of millions per year. For a cell phone, I would say that the criteria that the platform is considering in order is first cost, and that's why you see the antennas on cell phones not only are small but multi-band, and their placement and their optimality is compromised, and so much of the GPS receiver processing in cell phones is really directed at compensating for such size, spacing, and bandwidth compromises in the antenna. There is a lot of RFI in a cell phone, primarily from other radios, but that RFI often is dealt with digital filters in the radio front end. The issue of jamming in a cell phone, I don't know that it's quite such a concern at this point. I think cell phones are willing to trade off some availability in the presence of jamming for driving down the cost, driving down the battery the power consumption. There isn't a whole lot of space. I think if an adaptive antenna could compensate for poor adaptive algorithms could compensate for poor antenna design, you might see them. And if availability in some critical applications was important, you might see it there. But otherwise, it's a bit of a tough sell, I think, in the smartphone space. Thanks, Mark.
Great, thanks, David. JD, anything to add to that before we carry on?
Yeah, I think I will agree with Dave that at least in the near future, I don't see adaptive antennas being used in cell phone. There may be some other techniques which we may use to get rid of interference, which could be a frequency domain excision or even transversal filter, so that we put nulls in at given frequencies. That may be happening in near future, but adaptive antenna not in near future.
Okay, great. I think we'll stop there for now, but do keep those questions rolling in. We do have a longer Q&A session again towards the end. Before we get to our next part of the presentation, I'll throw it back to Lori for our second poll question. Lori.
Absolutely, folks. Coming up on your screen is that next poll question. We'd like to hear from you. If you'd go ahead and weigh in. Should a GNSS antenna be designed for smallest possible bandwidth to filter undesired signals? And go ahead and select one, yes, no, or don't know. And there we go. Looks like we have yes as a bit of a front runner, no just following, and don't know in third. Mark, any thoughts there on those poll questions?
Well, I think that also speaks to the fact that there is a bit of uncertainty around some of these aspects of antenna design and what in this particular case, bandwidth, what role that plays. So hopefully you'll gain a little bit more insight to that as we go forward. So on that note, we will continue our presentation now. I'll turn it back over to JD, who's going to talk a little bit more on the hardware part and the antennas, but this time looking more at the geometry of the antennas and the effect that has on performance. So JD, back to you.
Thank you, Mark. In the first part of my presentation, we talk about the antenna aperture, and within that aperture, how many elements should be there and how it should be distributed. Next, I want to get into what kind of surface do we want? Do we want a planar surface or non-planar? Most of the adaptive antenna you will come across these days, they have a planar aperture or maybe very slight curvature to them. If you got a planar antenna array, you know in the other dimension you don't have any much of an aperture. So that means you don't have a whole lot of resolution in the other direction. Let's say my planar antenna is a horizontal antenna. Then I don't have that much resolution in the vertical plane. To increase the resolution in the vertical plane, if possible, we want to make an antenna non-planar. A lot of work has been done in this case. And what people have found, convex non-planar array, they give the best performance. Also, once you make a surface non-planar, you have more surface area. Now, you can add more antenna elements to your aperture or to your antenna array to get better performance. So what we are going to do is, we will take these 6 antenna arrays and we will study their performance under different jamming conditions. The top 3 antenna array, they have 7 elements. The bottom 3 antenna array, they have 10 elements. All of them have about the same aperture. The one on the left are planar. The one in the middle have a convex surface. The 2 on the right, they have concave surface. And we are going to study the performance in the presence of interfering signals. So to study that, what was done was, we calculated the pattern, gain and phase response of various antenna elements in situ using a numerical code called FECO. Once we have the volumetric patterns of various antenna elements in the band of interest, we study the performance. Because I'm using the whole antenna array, mutual coupling, structure effect, everything is included in this evaluation. So this chart tells you this kind of signal scenario we used. We have a desired signal and multiple interference signal. We are going to move the desired signal around to cover the whole upper hemisphere. And this signal is quite weak, minus 30 dB signal to noise ratio. And interference is very strong, and it is coming around horizon. I'm going to show the results average over 25 trials. And for each of these trials, the interference direction was varied randomly. In this performance, we are going to look at space-only processing, not STAP, like David pointed out. And we are going to assume all the interference signals are narrowband or CW tones. The performance will be same for wideband signals also, as long as we start using STAP instead of space-only processing. So this chart tells you the performance of the 6 antenna array when I'm doing simple null steering. Basically, I'm keeping the weights of the center element fixed, and I'm adjusting the weights of other antenna elements to put null in the interference direction by doing power minimization. The plot on the left is for 7-element antenna. The plot on the right is for 10-element antenna. So let's look at one of these plots. You can see the convex antenna, green curve, has the best performance. The next is planar antenna, the blue curve, and the concave antenna has the worst performance. Also, as you go add more antenna elements, you move from left chart to right chart. And you can see, again, convex antenna has the best performance, and other two antenna, they don't give as good as performance as we want, and the concave has a really bad performance. Other thing you will notice, when I went from 7 elements to 10 elements, the concave antenna, the red curve, its performance degrades. This is what I was alluding in part 1. We are adding more elements in a given aperture or on a given surface, and that increases mutual coupling. And for concave antenna, that curve, antennas are just facing each other. They are very, very strongly coupled. And then you add more of them, you got a very strong coupling. And you don't have upper hemisphere coverage from the center element anymore. And that is why, even for one interfering signal, you are starting very low. As you increase the number of interfering signal, for the 10-element antenna array, performance is now degrading too much because we have enough degrees of freedom. As a matter of fact, with 10-element antenna array, you can have more interfering signal like 7, 8, 9, and you can still get 15-20% coverage. However, in the absence of interfering signal, because of mutual coupling, you can see the performance degradation. That was when the antenna was used in simple null steering mode. But we can also use the antenna in the beamforming / null steering mode, which David pointed out in the morning. And this chart shows you the performance of 6 antenna arrays in the beamforming / null steering mode. Again, green curve is convex surface, red is concave, and blue is a planar antenna. Again, we see convex antenna, as expected, is performing much better. Performance degrade as you increase the number of jammers, which is again expected. And in this particular case, now when we go from 7 to 10 elements, we move from left chart to right chart. Now you can see for all 3 antennas, performance is improving. So if you pack more antenna elements in a given aperture and you don't do something to get upper hemisphere coverage, you better go for beamforming / null steering to get better or the best performance. So that was about what kind of surface we want. And I'm sure you will agree with me, it should be convex surface if we can deploy or mount a convex antenna on a given platform. The next thing, which will answer the question you guys just answered in your poll, how should we select the antenna element? Because if your building block is not good, the whole building is not going to be very good. So first thing is, you want these antenna elements to provide the upper hemisphere coverage because you're going to receive satellites from the upper hemisphere. Second thing, please do not design your antenna elements to remove the interference. You should always design your antenna elements for a little bit larger bandwidth. First thing is, in a GPS receiver, you're trying to measure encode and carrier phase. And if your antenna has a very small bandwidth, it's like a filter, it's going to distort your signal quite a bit. That means your measurements can be in error. So that's one reason. Even if you have a single element antenna, please don't make it a filter. Second thing is, by having a little bit more bandwidth, I can have a very stable phase. In our case, we are dealing with adaptive antenna. If my antenna have a larger bandwidth, I don't have to do a lot of signal processing to put nulls in different direction. Basically, what I'm saying is, an antenna element is a dispersive component. Then we put coupling between the antenna elements because we are going to put a lot of antenna elements in a small space. Now, what you have is dissimilar dispersive received signals. And if you're going to do destructive interference to null the interfering signal, you can see your antenna electronics has to do a lot of work. Somebody can say, oh, I'm going to just add more taps to my step processing to take care of the dispersive nature. Yes, you can do that, but the cost of signal processing has increased. Also, in the first part, I talked about antenna-induced biases. If every antenna element looks different, then the antenna-induced biases in the presence of interference signal as compared to the antenna-induced biases in the absence of interfering signal will be very, very different. So your calibration of the antenna in the absence of interfering signal will not hold in the presence of interfering signal. So even if I can make up by using STAB in terms of nulling performance, you're going to pay in terms of antenna-induced biases. To give you an example, let's take a simple antenna array with 6 elements. And these elements are distributed on a circle of about half a wavelength. Elements are coming out of the plane of the paper or out of the plane of the screen. And for this particular case, I'm going to use 2 gigahertz as my center frequency. You can use L1 band signals also, but I just use 2 gigahertz. And I'm going to use either of the 2 antenna elements shown at the bottom of this slide as my choice of antenna element. One is a thin dipole, another is a biconical antenna. Both are designed to receive signal at 2 gigahertz. This chart here shows you the gain and phase of the 2 elements in a selected direction as a function of frequency. You can see biconical antenna, the red curve, has a little bit flatter amplitude and flatter phase. So it has less dispersion as a function of frequency. So to study the performance of these 2 antenna array with a different antenna element, I'm going to put a strong desired signal in the XY plane. Strong means 0 dB signal to noise ratio, stronger than regular GPS signal, and it has a 50 megahertz bandwidth. Then I'm going to introduce 3 interfering signal, which are much, much stronger with 50 dB above the desired signal. And in this performance, again, mutual coupling is included in the evaluation. And this chart here shows you the performance of 2 antenna array. The plot on the left is when I'm using thin dipole as my elements. The plot on the right is showing the performance when I'm using biconical elements as my building block. You can see, first thing, both antenna array have null in the 3 interference direction along 10 degree, 130 degree, and 240 degree. Biconical antenna array has a little bit sharper null. Then let's start comparing the performance. If the incoming signal, the jammers, have no bandwidth, then the 2 have same performance. Because when jammer has no bandwidth, the dispersion does not play a big part. As soon as the interfering signal or the jammer have some bandwidth, like 10 megahertz blue curve, you can see the performance difference. You can get almost 10 dB better performance using these antenna elements with a little bit larger bandwidth. If we are going to 50 megahertz interfering signal, you can get almost 12, 13 dB better performance in certain angular region as compared to the thin dipole. So what it means is I may still be able to receive some satellites even if I got 3 interfering signals. So to conclude, what I'm trying to say here is if you have a choice, go for a large aperture. But we know these days everybody's looking for aperture to put their antennas, so we don't have that much choice in terms of the aperture size. Normally we deal with a small aperture. You've got a small aperture, you should put elements, as many elements as you can. Hardware cost, and the size of individual antenna element will tell you how many elements you can really include in that aperture. But please do not make the antenna element spacing more than 4/10 of a wavelength or half a wavelength, otherwise you will get grating lobes. Also, if possible, don't have a planar aperture. Make it a convex surface so you can have resolution in azimuth as well as in elevation. Finally, when it comes to selecting an antenna element, please don't make them as a filter because you're going to pay a bigger price. You may be able to remove some interfering signal, but you're going to pay a bigger price in terms of accuracy of your solution. Thank you very much. Back to Mark.
Great, thanks a lot, JD. I'm going to turn it back over to David to show some kind of practical results. We've seen a lot of kind of theory and concepts, and David's going to show us a little bit about the results and perhaps a bit of a glimpse into his crystal ball as to what he sees coming down the pipe. David.
Thanks, Mark. So now we've learned quite a lot actually about multi-element and adaptive antenna systems for GPS. And JD has covered numerous practical aspects of antenna array design and layout geometry. At this point, it's probably a good opportunity to talk further about testing these adaptive arrays. After all, we may at one point be interested in specifying, selecting, or verifying an adaptive antenna system for our own GPS product. The most obvious way, and certainly where one would expect to spend a lot of energy and effort, would be in numerical simulations, creating computer models of the signals, jammers, antennas, front-end electronics, and the GPS receiver. I think, though, that it's instructive for us to start a discussion at least one stage beyond this all-software approach. After all, numerical simulations will give us predictions regarding anti-jam performance, but it's only when we introduce some degree of hardware into our test regime that we begin to gain real confidence in our numerical predictions. Particularly of interest to us is testing candidate weight control algorithms against varying levels of jamming, different RFI waveforms, and jammer geometric distributions, as well as exploring the response of the GPS receiver. For example, tracking biases, jitter, and margin. Therefore, what you see illustrated here is just one such scenario. We have recorded live satellite signals through our array, and we play them back in a software environment where we can overlay RFI of any desired characteristics. So in this way, we capture some analog effects, including timing biases and cable delays, but we're unable to directly observe saturation or other nonlinearities which may be caused by high-powered jamming signals. Still, it's a reasonable place to start, and has another advantage of being relatively low cost and low effort. For example, one could conduct the signal recording part of this test using simple software programmable radio front ends, such as the fairly inexpensive USRPs that many of us now have in our labs. Then, playing back the recorded signal, we can overlay any desired level of interference in jammer waveform. That's what you see here. We've played back our recorded signals, but superimposed also a jammer 45 dB more powerful than our satellite signal. In this way, we can compare apples to apples for a single antenna receiver, the red trace, a deterministic beamforming Serpa, the pinkish trace, as well as our fully adaptive beamforming and null string Serpa, the MVDR blue trace. I say apples to apples since we truly have isolated any improvement due to the array. We're not confusing the effects from other anti-jam hardening, such as inertial aiding or frequency domain adaptive filtering, which may arise if the signals are processed through different receiver architectures. Another method of testing is to synthesize both the signals and the interference for injection directly into the RF front end of a receiver. This does not pass the signals through the operational antennas, but it does exercise the front end electronic components, filters and amplifiers, and the analog to digital converter, saturation and dynamic range having such a critical impact on system anti-jam performance. In fact, depending on the interference type, if the A to D converter saturates or does not have enough discretization levels, then our anti-jam efforts can be doomed to failure no matter how clever our beam steering algorithms are. In any case, the system illustrated here on this page is now quite a complex experimental setup. In other words, not for the poorly funded or faint of heart. But it does allow precise and repeatable testing in a laboratory environment with operational hardware in the loop. The next method is anechoic chamber testing. Now, the entire receiving system can be exercised, from the antennas through to the receiver's PVT output. Of course, the output from just the beamforming operation can be analyzed separately to look specifically at anti-jam performance, or attenuation. The image on the left is from testing for antenna response characteristics in a chamber at Ohio University. The images on the right show even larger chambers, suitable even for full-size vehicles, as you can see in the lower figure. Chambers such as these are excellent candidates for careful, controlled, and highly repeatable test campaigns. For example, the recent testing of interference effects from LightSquared's proposed nationwide L-band terrestrial network. The drawbacks to such testing include the fact that these are expensive and specialized facilities and are not readily available to all research teams. The final test environment I want to mention is live over-the-air jamming trials, such as are conducted at restricted military areas. After all, in the US at least, it's not such a good idea for us to fire up our GPS jammers and radiate interference. This testing, as you can imagine, is fairly high stakes, meaning that these events come along infrequently. They're expensive to conduct and even to participate in. They involve lots of planning and travel, and typically you're up all night in order to minimize the potential impact of GPS jamming during normal working hours. Finally, there are no do-overs. You only have one shot, so if equipment failures occur, then you may end up losing part or all of a valuable testing opportunity. Our team from Stanford University has been fortunate enough to have participated in a number of such trials, and I've got to say, this one here at White Sands Missile Range was one of the nicest. Beautiful evenings under nighttime summer skies in the high deserts of New Mexico. This next slide shows one of the test scenarios from this event. This scenario had two dynamic jammers mounted on the trucks you saw on the previous slide, with one truck in the lead and the other in trail. As the trucks drove down the highway, our test equipment, which was situated within about 5 meters of the pavement, recorded and processed the live satellite signals as well as the jammers. The output traces on the right side of this viewfoil show the J to N power ratio in the blue curve, which spikes upwards each time a truck passes in front of the test site, as well as the processed carrier-to-noise power density ratio for several different beam steering techniques. I should emphasize again that all of this performance data was available to our team in real time, and as well we could replay it from stored disk files in our lab in post-processing. I'll close this section with that observation, that the most important procedure we implement in all of our live jamming testing has been the recording to disk of all scenarios for post-processing replay analysis. Okay, we're on the home stretch now. This last topic area is to bring everything together and to consider in a larger context the threats and objectives we're actually trying to address with an adaptive antenna system. We've touched on this next part already, but it does bear repeating. GPS signals reach the receiver at very low power. This image comes from Chris Hegarty and was generated to illustrate in what spectral neighborhood GPS signals reside. For us, it reminds us that we need to consider a number of potential sources of interference. High power signals from in nearby frequency bands, accidental or unintentional in-band interference, and finally deliberate jamming, including wide area denial of service attacks. In fact, I think it is instructive to break down more formally the interference threats facing us. One way of doing this is to classify them according to this matrix, which admittedly is biased toward the civil receiver outlook. In the upper left corner, we have scheduled outages, things that our GPS service provider is aware of prior to their occurrence and for which continued service of the utility is not guaranteed. This would be events such as the jamming exercises conducted periodically at White Sands Missile Range. To the right, we have short-term anomalies, hardware faults, or other inadvertent events, basically unforeseen faults so severe that continued service may be disrupted. This could be things like the high-power military comm system which jammed GPS signals in San Diego in January of 2007. In the bottom row to the left is low-power jamming, for example from personal privacy devices or PPDs. This could be things like the well-publicized disruption of the LOS system at Newark's Liberty Airport. And finally, to the right is deliberate high-power jamming. I contend that the first three categories should be addressed nearly completely by anti-jam technology in general and by adaptive antenna arrays in particular, so long as the RFI source is not unreasonably close by. Of course, for the ultimate in reliability, some sort of ride-through or fallback capability may be advisable. For example, for aviation, there's the FAA's alternate PNT program. Thus, these first categories would represent little more than a nuisance to a properly hardened GPS receiver, leaving us with the lower right quadrant. Our goal, then, is to harden our receiver to the maximum extent possible, given our mission requirements, budget, and other constraints. Basically, to push an attacker as far to the right as possible, which essentially means either that the attacker's zone of influence shrinks dramatically, either in space or in time, or that they are forced to radiate at elevated power, making detection, location, and mitigation feasible. With that thought in mind, I think this next chart should be clear. Essentially, what this does is to describe the various operating states for our robust, jam-tolerant GPS receiver. What I show here is that the receiver starts in a conventional single antenna state for initial power on, startup, signal acquisition, and tracking. It then transitions to a multi-element mode, first going through a temporary pull-in state to transition through any large transients caused by the switch to array processing mode. Once the transients are settled, the receiver enters into its predominant operating state, steady-state standby mode. During this steady-state mode, our receiver can be monitoring and updating correction models for various biases and errors that it may experience, such as, for instance, differential cable delays, antenna biases, and other hardware nonlinearities. If and when jamming occurs, then the receiver transitions automatically to RFI rejection mode. While it's likely that the adaptive processing reacts automatically at this point, there may be other receiver changes occurring as well. Perhaps things like changes in tracking bandwidths, altered covariance settings in the navigation filter, and additional cross-checks on decoded navigation data. Whether the receiver loses lock entirely and reverts to open-loop coasting, or can return directly to the standby mode of operation, will be a function of the severity and duration of each RFI event. This image shows the hardware implementation of just such an adaptive antenna GPS receiver. In this case, one developed by my colleague, Dr. Yushan Chen of the Stanford GPS Lab. The stack of devices in the upper picture are the now ubiquitous USRP software programmable radio front ends. This gets signals from the antenna array into digital samples that can be processed by the small workstation computer in the bottom picture. I want to emphasize several things here and in the next slide. First, that this research platform was built exclusively with inexpensive, commercial off-the-shelf parts, showing an existence proof of a low-cost, multi-element adaptive beamforming and null string GPS receiver. Second, that we're at a stage now in terms of raw computing power that all of the processing can be done in software on a general-purpose CPU. It doesn't require hardware offload or special-purpose DSPs. And third, that all of the array calibration can be done online in real time by the allocation of massive numbers of receiver tracking channels. That's what this screen shows. This is a screen grab of the primary user interface to the receiver from the previous slide. This receiver implements a tracking channel for each satellite and each individual antenna element, strictly to compute array geometry and to observe antenna and cable biases. So with 12 satellites and 4 antennas, we're talking 48 tracking channels just for the real-time calibration of the array. Next, this research receiver implements both a power minimization adaptive nuller with 12 satellite tracking channels, as well as MVDR with individual weight vector computation for all GPS satellites in view, for another 12 tracking channels. All of this is done, of course, with 14 bits of sample resolution. And I really do want to conclude here. A number of anti-jam options are available to a GPS receiver designer, some more effective and more expensive than others. Multi-element adaptive antennas are among the very strongest interference mitigation techniques that exist. And the proper approach is to define the mission objectives, then evaluate vulnerabilities and threats, and finally develop an appropriate response. Thank you all so much for your time today. It's back to you, Mark.
Great, thanks a lot, David. Obviously, you guys have done a very good job of presenting a lot of material, and from an audience perspective, that might be difficult to all soak up at one time. So for those of you in the audience, please do note that there are some additional resources that will be made available to you. These include the PDF versions of the presentation of the slides that you saw today, including a few extras, as well as a bibliography that the panelists have put together to kind of give you a place to start for looking at a bit more of the details. And of course, there's some contact information there if you are interested in contacting either of the panelists directly, or if you are interested in visiting our sponsor's website at novotel.com. So before we get into our last Ask the Experts Q&A session, I'm going to turn it back over to Lori for our final poll. Lori.
Perfect. Thank you, Mark. And folks, coming up on your screen is that final poll. And we would like to ask you, what are your top 2 concerns regarding the use of a multi-antenna setup to mitigate jamming and interference? Now, in this case, you can select more than 2, but we're asking you on your honor system to go ahead and give us your top 2. And we'll share out the results again so you can see where you fit in among your colleagues. And we'll share out the results. There we go. So it looks like there's a nice smattering on the results there. Mark, any thoughts on what you see here?
I think this speaks very much to the very rapid expansion of GNSS and positioning technologies into low-cost, small devices such as cell phones and vehicles. So perhaps not overly surprising, and hopefully some of the things that you learned today will help you kind of address some of these concerns, or at least perhaps look for other alternatives if they don't directly. So having said that, I think we'll go right to our Ask the Expert section. Now, we've had several of our audience members chime in, so hopefully we'll try and get to as many of these as we can. And we're going to start with you, JD, a question from Michelle, who said, if you combine, say, n individual antenna radiation patterns to cover better the upper hemisphere, how many degrees of freedom do you have left for mitigating interference?
Thank you, Mark. That's a very good question. I think Michelle is talking about my last chart in part 1, where I showed that 4 and 5 inch antenna array with 6 elements. The answer to Michelle's question is we still have n-1 degrees of freedom. Think about this, Michelle, that we are putting a beam along zenith, and then we are trying to null the interfering signal. So it's the same thing as beam pointing / null steering. So I'm putting only one constraint. That means I still have n-1 degrees of freedom. So by doing that, by combining antenna elements to get the upper hemispherical coverage, you are not losing anything.
Great, thanks a lot, JD. David, the next question is for you. This one's from Paul, and he was wondering whether or not you can do beamforming without an IMU, which you had showed on one of your earlier slides in the first part.
Thanks, Mark. That's interesting. Of course, we've talked about constraining the pointing direction of the array, giving knowledge of where you are and where the satellites are. If you don't have an IMU, another way of doing it is to use characteristic of the signal itself. A least mean square beamformer is certainly one option. I think it's as JD would point out, probably gone out of vogue a little bit in the last few years, but you certainly can synthesize pointing constraints using known characteristics of the signal. Thanks. And JD, please feel free to chime in if you want as well.
I think Dave has done a good job. Thank you.
Oh, thanks.
Okay. Great. The next question I'm actually going to direct to Neil from our sponsor. We've actually had several people chime in asking very related questions, and afterwards I'm going to ask whether or not Dave or JD has anything to add. So the question is about the role of dual use purposing of multi-antenna arrays, and kind of what the implications are this for commercial systems, and whether or not there may be any export limitations that people need to be aware of.
Okay, hi Mark. Yes, for one thing, dual use, that's a term that comes out of the US ITAR conventions, and strictly speaking, null forming is covered by the Wassenaar Agreement, and so companies that agree to the Wassenaar Agreement on export dual use proliferation must follow those export rules. So for example, in Canada, the antenna arrays, when we create the gadget anti-jam antenna, it's a null steering antenna. It is covered by Canada's export regime. If people are worried about ITAR, that'll come down to a case of, is there US source technology in there? So in our case with Gadget and other things we develop in Canada is not ITAR, but we still must abide by Canada's export regime because it's a null steering use. If there is no null steering involved, then you could make an argument to your in-country export regime as to whether that falls under the dual use category or not. In all cases, we as a manufacturer have to abide by our countries and other countries we ship to export regimes, and you'll want to check with your export compliance officer at your company to make sure that you're always following the export compliance, because they are governed by the overall Wassenaar Agreement. Thanks, Mark.
Yeah, great. Thanks, Neil. Dave, anything to add to that?
Not a whole lot, Mark. I think Neil pretty much covered it. I do know that it is a concern, and for us at Stanford, doing research on adaptive antennas and multi-element arrays, it was a concern, and I know we worked closely with our university IT office. IP and legal office to find out what constraints we had on. First of all, of course, publication of research results, sharing of code, and then moving things around as we shipped for testing purposes. So it is a big concern, and I'm certainly not an expert, so I defer to Neil and you guys on that. Thanks.
Okay.
And David, if I could add on to that, we've found too that it's not an insurmountable problem if you follow the rules and apply for the permits. Things can move very fast, and certainly government export regimes are getting more and more used to the technology of null-forming GNSS antennas. So we're finding that export permissions are not taking long at all now. Thanks.
Okay. JD, they've obviously given a pretty good response. Anything to add to that?
Yes, as Neil said, it is law of the land, and we have to follow those laws. We have to make sure that we don't buy or sell something which we are not supposed to.
Yeah. Very good. All right, JD, the next question is going to be directed at you. The question is, when there are no jamming signals present, is the positioning accuracy of DGNSS, or presumably just GNSS system with an array, as good as with a single element? And does the signal-to-noise ratio have a role there?
That's again very good question, and the short answer will be yes. Using an adaptive antenna or antenna array will not affect the accuracy of your differential GNSS system. As a matter of fact, if you're doing beam steering, you can reduce the variance in your measurements because carrier to noise ratio will go up. So adaptive antennas, in the absence of interfering signal, also can be used to get better measurement by beam pointing. Thank you, Mark.
Great. Thanks a lot, Judy. David, next question for you. This one's sent in by Len. He's asking an interesting question here. Can you use the National Cell Tower GPS receivers to actively locate interference, with the idea being that this would be potentially useful for making users aware of the problem, even if they don't have the technology built into their own receiver?
Thanks, Mark. That's interesting. I mean, we hear a lot about the potential of using sort of large networks of installed infrastructure to detect, possibly to locate interference. And so I think it's certainly a possibility. Certainly the current network of cell tower GPS receivers would not be suitable for that. One would have to imagine a at least new software architecture, possibly new hardware. So I think it's an interesting thought. Certainly not going to happen in the next couple of years. It would certainly require probably a lot of government rulemaking. But there may be a place for it. If interference becomes enough of a concern, perhaps the cost and complexity of doing that would be worth it. It's certainly not in the next couple of years, though. Thanks.
Okay. Great. Thanks a lot, David. Jitty, next one is for you. This one's sent in from Tim, asking about, and in fact, we've actually had several people asking questions related to this. When selecting wavelength spacing for an adaptive array on a multi-wavelength system, or perhaps to elaborate on what other people are talking about, a multi-GNSS system, should you simply average the largest and smallest wavelength or apply some other technique?
Yes, what Tim is asking about is, let's say I have an antenna or antenna array, and we want to receive L1 as well as L2 signal. As you know, L1 is 1575 megahertz and L2 is around 1227 megahertz, something like that. So there is quite a bit of frequency difference or wavelength difference at the two bands. So, and I kept on telling you, keep the separation half a wavelength. So what should we do? Now, if you really want to go with theory, you should use the highest frequency as your criteria. So I will be using L1 band 1575 megahertz, which translates to about 20 centimeter as my criteria. So I will not put elements more than 10 centimeter or so apart. So to get the best, that's what you want to do. But that means I will be packing more elements. So at L2 band, you will have more coupling between antenna elements. But if you're going to do beamforming / null stirring, as I mentioned before, that coupling can be taken care of. So theoretically, to get the best performance, use the smallest wavelength you're going to deal with. But some cases, you do make a compromise. You may want to select somewhere in the middle. That's it then, Mark.
All right, thanks a lot, JD. David, next one's directed to you. This one was sent in by Lay. The question is, how important is phase center variation, and what design considerations are needed to reduce phase variation?
That's interesting. Thanks, Mark. So JD is probably more of an expert on the antenna design to reduce phase center variation. I'll say that I would consider two approaches to combat the reality. One, given what you have in your hardware design, one is the online calibration I talked about, where at least for our architecture, we allocate receiver tracking channels to observe in real time the phase difference. Basically, what you do is you track the satellite on two different antennas, and you can observe the carrier phase bias due strictly to the antenna, since you know the geometry and you know where the satellite is and everything. And then you apply that you store that in a lookup table, and you apply as a correction in real time. The other thing I would say is that certainly designs that minimize the phase center bias to begin with are of course preferable. And so that's what I would say to that. And JD, if you have anything to add.
Yes, if I understand the question is when I'm designing individual antenna elements, how much attention should I pay to the phase center variation? Normally these antenna elements are fairly small, and they do have some phase center variation with respect to elevation angle, if not with the azimuth angle. And as Dave pointed out, the best solution is calibration. You calibrate the system. However, for adaptive antennas, this calibration in the absence of interference sometimes does not work when the interference comes in, because we are going to combine various antenna elements using weights which we don't know a priori. So for adaptive antennas, if you really are going to go for accurate measurements, accurate carrier phase measurements, there are two approaches you can follow. One approach is you estimate the biases introduced by your adaptive antenna on the fly, and it can be done. We have done some work in that. Basically, you calibrate individual antenna elements, you calibrate the front end, then you read in the real-time weights, and using all that information, you can estimate how much error my antenna is going to introduce in the process of nulling and beamforming. So that's one approach you can use to get rid of it. Second is you can also design your weighting algorithm, the way you calculate your weights, so that antenna-induced biases are minimized. So those are your best approaches, either real-time estimation or selecting the weights to minimize the antenna-induced biases. Back to you, Mark.
Well, thanks a lot for the excellent answers from both of you, actually, on that one. David, next one to you. Is there any software solution for the problem of refraction or reflection when using the antennas in areas where there are buildings or strong reflectors? And that was sent in by Tarek.
Thanks, Mark. So of course, what you're talking about is multipath, and strong reflections from buildings and other reflecting surfaces will be a problem for a single antenna receiver and for a multi-antenna receiver, depending on your weight control architecture. Certainly for the ones I talk about, which use signal properties for beam steering, will suffer greater due to multipath because they'll lock on a beam onto the multipath signals as well and boost them. The architectures we talked about, which do constrained beamforming towards satellites, will enhance. Of course, multipath is a function of the signal to multipath ratio, and if you're beam pointing towards a signal, you'll have boosted the signal at the expense of multipath, and so you'll benefit there. There are, of course, also ways where you can observe in real time multipath components and then null steer to them. So I think there are solutions, either just relying on the characteristics of the beam pointing, or you can estimate and null steer to multipath signals. Thanks, Mark.
And great, thanks, Dave. I think that's really interesting to kind of take a more of a civilian look at the problem, if you will, as opposed to kind of the intentional jamming aspect that we typically concern ourselves with. I think we have time for one last question, and I'm going to direct this one to JD. This one is from Pavel, who asked the question, can you please explain the importance of the field of view of a single antenna element?
Yes, Pavel, that's again a good question. Let's start with beamforming. I want to get high gain in the direction of a given satellite. And we know satellites can be up anywhere in the upper hemisphere. So if I want to get the maximum gain out of a given antenna array, that every element should be seeing that satellite. That is the only way I'm going to get the best that improvement in my gain. So from beamforming itself, you want to have all the elements having a good upper hemispherical coverage. Now, to answer the second part, nulling part, I'm going to go back about 30 years ago when I got into this adaptive antenna business. One smart guy, he said, oh, we have a smart antenna. I can put antenna elements at one on the top of the aircraft, one at the bottom of the aircraft, and I can do my nulling. Well, the two antennas, they are seeing very different RF environment. There is no way you can do the nulling. So basically what I'm trying to say is, even for nulling, if there is only one antenna element which is looking in the interference direction, you are limiting yourself. On the other hand, if all the elements can see the interference, you are in a better shape to put a null in the direction. So that is the reason for adaptive antenna. As a matter of fact, any antenna array, when you're going to build an antenna array, you want all the elements to have good coverage in the desired field of view. Back to you, Mark.
Great, thanks a lot, JD. And in the interest of time, I think we'll call it quits there. Before I turn it over to Lori, I'd like to thank our panelists, Dave and JD. I think you did an excellent job. And also, on behalf of myself, I'd like to thank everyone for listening and hope you've learned something. And again, do remember that there are some resources available online or will be shortly that you can follow up with. So, Lori, back to you.
Fantastic. And folks, it is about time to wrap up. We're going to go ahead and invite Neil Guerin, our sponsor from Novotel, to leave us with a brief words. Over to you, Neil.
Thanks, Lori. Thank you to everybody out there for joining us today, and special thanks to our panelists, Dr. David Lorenzo and Dr. JD Gupta, and to our moderator, Dr. Mark Petavello, for an excellent presentation. Novotel is working on behalf of our customers to provide the most interference-robust solutions possible for a wide range of civil and military applications. For more info on Novotel's precise positioning receivers and antennas, please visit Novotel online at www.novotel.com. Back to you, Lori.
Thank you, Neil. And folks, again, you will be receiving a short survey at the end of the webinar. If you take a moment to fill it out, we certainly appreciate your time and feedback. Also, I'd like to issue a special thanks to our logistics producer, Patty Van Hooser, for her behind-the-scenes collaboration and support. A copy of today's webinar will be available for download, and you'll receive it in the way of a link via email early next week. And most importantly, thank you for joining us. This is Lori Dearman saying have a great rest of the week. Bye for now.